Okay, thank you very much. I'm going to talk about quite a lot of history and some futures, and also the inspiring interactions I had with Ken Kennedy and the Center for Research in Parallel Computation, which was devoted to making parallel computing easy to use and very powerful, and had a lot of activities in that area. I should note that I didn't actually start I started in big data. Namely, when I was a beginning graduate PhD student, my supervisor told me, nobody looks at data, please look at data. So actually for the next 20 years, I looked at data. And I made models and tried to understand that data. I also, because I used computing the whole time, I decided to leave England, where I thought I'd stay, and come to the US. And I was in the field called phenomenology, which meant you made models. It was a field which was typically, in those days, not very well respected. But at least at Caltech, where I was, it was respected. I should note that we have all these, we now realize the importance of statistics. I actually taught the first statistics class at Caltech in 1980 around, and it actually is not so far behind what we see today. And in fact, at that time, if you wanted to know about maximum likelihood and things, you had to go to particle physics note, because that's where all the big data analysis was done. All right. So then Carver Mead changed my career. He also changed Tony Hayes' career, my colleague, when he gave a talk at Caltech explaining to the physics department why VLSI would make parallel computing inevitable. So here is a little comment on data science. So actually, I think phenomenology is actually data science. Actually, data science is a better name, because I can't pronounce phenomenology. But anyway, here is a paper that I write papers with Tony Hay every 10 years. This was our first one in 1971. It was a proceedings. And we define phenomenology, and we make various comments about the difficulty of making theorists and experimentalists talk to each other and things like that. So it's not so far from being the same as today. So here is an interesting comment. So this comes from 1978, when I had a very talented colleague called Stephen Wolfram, who was formerly my student, but I was really his student. And we had these so-called moments. And they are actually a pretty highly cited paper, still used. But unfortunately, they're now being replaced by deep learning. In fact, everything is being replaced by deep learning. And you see the Fox-Wolfram moments at the top. H2 is the most important. And then CMS have come along with JediNet and replaced them by a deep learning network. And you can actually see from this picture here what these moments and or is their replacement are meant to do. They're trying to look at the structure of a complex particle physics event and be defined in a way that's insensitive to the way the jets or the quarks or the gluons or the Higgs or what have you decay. So they're sensitive to structure. And of course, deep learning is very good at structure, so it's not surprising it's going to replace it. All right, so that's... here is I spent actually some time being an experimentalist. I decided that it didn't seem much sensible for experimentalists to make models and interpreting their data, and then along came phenomenologists and made new models, so I tried to work from the beginning with them. And I did 3 experiments at Fermilab. I won't dwell on it, but anyway, these were the models we made to fit these experiments. One of them was the field Feynman-Fox model, which was a model for high transverse momentum scattering. And at those times, I used to work quite fruitfully with Richard Feynman. All right, so then we had this famous colloquium by Carver Mead, and then I teamed with Chuck Seitz and we built the Hypercube machine, which was pretty powerful, comparable to the Cray's, and it was called the Cosmic Cube. And the top is the one which Chuck Seitz built, and the one below is the one built by JPL. That even resonates with the keynote yesterday, because we used to do parallel image processing was one of the areas we looked at in those, and we were looking at image processing for the Mars rover. So then, in looking to the future, here was a talk I gave in 1988, and I looked at 84 applications, and it's sort of interesting to see what I deduced, that about 40% were SIMD, because in those days we had CM2, we had mass pars, and we were debating whether SIMD or MIMD was the right way to go. And looking to today, there's 14%, which I called embarrassingly parallel, but now we call pleasingly parallel. And actually, we didn't really recognize in those days that that category was actually grow and probably become the most important category, numerically at least, in high throughput computing. And so that's some interesting little bit of history. Then we had the Center for Research on Parallel Computation, which was started in 1989 and ran through 2000. And that had a major activity called High Performance Fortran. And we worked very hard on that, and really we didn't actually really catch on with that, because although it could do all the problems that were around at the time we started, it couldn't do the nifty new, very dynamic problems that were produced by the grand challenges. In that time period, there were a lot of grand challenges from NASA and NSF and DOE, and they built very adaptive programs that were not so easy to write for HPF. We also tried to look at other languages, but that didn't catch on. So people have complained about my suit. I point out that I was wearing a suit in this short course. This was somehow one of the early 1994, so CRPC had made quite a bit of progress. I also chose a snap from the video showing transparencies being flipped around and show what skills we had to have in those days. And we have Jack there, and Paul Messina, and Ken, and myself discussing the cosmic picture, with the overall picture of parallel computing. So that was, and we actually produced a compiler at Syracuse. That was Alec Chowdhury led that, and that was licensed to the Portland group. So here is a pretty cheerful picture. On either, we have Ken Kennedy and myself as pictured by some artist in Colorado, actually in Colorado in '95. I have the corresponding pictures for all the other members of CRPC. I think I sent them to everybody. And in the middle, we have a picture of me in Athens, because this work I did with Ken Kennedy started in 1987 at the IEEE-CS conference. Actually, it started on a back seat in an Olympic Airlines flight back from Athens to the US. So that's why I don't have a picture of my interactions with him. I didn't take pictures in that particular airplane. We did lots of work on education. Here's various CRPC education activities. One of the advantages of the Science and Technology Centers is that they have a complete suite of activities from research and outreach. And so we did a lot of educational activities. So let me just quickly discuss HPF, which we spent a lot of effort on it. So using today's language HPF model was you take tensors and you decompose the tensors across the parallel tasks. You use the owner computes rule, that the processor that holds the data does the computing for that data. We build wonderful kernel libraries using MPI and OpenMP, and then we use the OpenMP for the threads. And as I pointed out, that would have solved the problems that CRPC, actually the world had in 1989. But as I said, we found that things like fast multiple methods, adaptive meshes, were not easy to express in HPF. And the other problem was it just is such a huge effort and a long time to develop a compiler, and it was not so easy to develop viable compilers for these different languages like Java and Fortran in a reasonable time. And so HPF never really became a standard capability, even though, as far as I can see, it can actually express large numbers of applications. I think, in my opinion, we gave up. We should have said HPF is good for, and the corresponding languages, other languages you might want to look at. And we should have produced it and had a more kept to the faith and produced this, because many examples today could use HPX and parallelize themselves, and are not parallelized. Maybe I'm wrong, but I think that's true for the training of deep learning applications, which tend not to run in parallel. They use data parallelism, not model parallelism, and I think the model parallelism could have been expressed in HPF. And also, I'll note at the end that the use of machine learning to capture fine-scale behavior of models could actually make programs look nearer the HPX model. All right. So what did we miss? Well, we missed, as I pointed out earlier, we didn't really have much focus on high-throughput computing, although CRPC evolved into the grid activity, which was largely focused on that area. And of course, high-throughput computing has a dominant cloud pattern and correspondingly a dominant grid activity. We miss big data. So I should have realized it, because as I said, I actually did data analysis for 20 years. And actually, big data is actually probably a little better for HPF than simulations, because there are no differential operators with data. And so you do not get these very difficult to express structures. And a lot of big data applications are actually somewhat easy to express in HPX. So one thing that's not clear to me with big data is, as I say, at the moment, I think most big data problems, if you look at, say, the model that Hadoop and Spark use for parallelism, it's even simpler than the HPX model. It's just simple decomposition. What's not clear to me is whether, as big data evolves, it will stay like that with relatively simple models, or it will be like applications, simulations. Because simulations, as I said, in 1989, we were able to do all the simulations with a simple model. But by 2000 came along, we couldn't do actually most of the important applications, at least not from the HPF model. So it will be interesting to see whether machine learning and deep learning become more sophisticated, or whether we're really just like 1989 for simulations, where we started simply and we're going to get incredibly complex. In my opinion, at CRPC, we got a little confused over distributed systems, namely the grid. And we were trying to do the same thing for the grid and parallel computers, whereas I think you want to do different things. And we should have, separated those two. I should note the grid is actually very healthy. It's now become a data grid, and it's called edge computing. All right, so now we move to the future. So we now look at how we converge big data and simulations in HPC. Now, sometimes when we discuss convergence, we don't really separate those ideas, but there is a separate convergence in pairwise in those areas. So if you look at HPC, it's quite obvious why HPC is essential for both big data and big simulation, because HPC makes things run faster. So how could that not be a good idea? And Geoffrey Dean gave a very important talk in NeurIPS in December 2017, where he discussed systems for machine learning and machine learning for systems. And this concept, or HPC, is useful for machine learning. I call HPC for ML, and it just is making machine learning run real fast. Another aspect of this convergence is the software area, where the Apache software stack and containers, which largely were developed for the big data, can now be used effectively with simulations. So now I want to shift to this other concept that Dean introduced, which is ML for systems, and he gave important examples from that time. And that is machine learning for high performance for HPC. And with my colleague Shantanu Jha, I've written a few papers on that, trying to analyze it. So let me give you a summary now. Let me skip that one. Well, actually, I should mention this one. Namely, what this chart says, it looks at big data problems and simulation problems and points out that actually the parallelism has lots of analogies. You have pleasingly parallel jobs, that's on the left in both cases. You have pretty easy to parallelize problems in the middle, the HPF style, and where you have a lot of linear algebra kernels. And you have on the left, you have really difficult problems like graph analytics. You're not going to do graph analytics with HPF, that's far too complicated. And latent Dirichlet allocations, those are complex big data problems, and there are obviously corresponding complex simulation problems. And for those, you're going to have to do user-performed parallelism, as far as I can see. So now let's look at this machine learning around high-performance computing. And it has three types of activities. The first is improving the computation by making the configuration better. So this is really an extension of auto-tuning, which was pioneered at Tennessee, and another related activity is data assimilation. So you can now do those somewhat better, or maybe a lot better, with deep learning and machine learning. So that's one class. More interesting class is actually learning the structure of the problem and the theory of the problem and making the models for computation. So the examples are learning potentials. There's a huge opportunity there because potentials are often very high order in the number of particles, for example. So if you can learn them, you can drastically decrease compute time. You can do coarse graining, you can learn microscale structure, and maybe we can derive fundamental theories. And another important area is smart ensembles. Do explorations of phase space in a more efficient fashion. The third category is actually sort of the simplest, but perhaps the most important. We just replace the simulation by not actually running the simulation. We just look it up in a deep learning network, and that's called surrogates. And the speed up you get is 2 from maybe the auto-tuning end, and for the surrogates and the learning the potentials and things, you might get up to 10 to the 8th has been reported in some examples. So these factors are huge, and that's pretty exciting. We will give some examples. So this is, so I choose an example that I sort of had something to do with, but there are many other probably better examples. There are a lot of people who have done this. So this is surrogates. This is a molecular dynamics simulation from the nanoparticle domain. And you can see it's actually not really a deep learning network. It's a multi-layer perceptron with just a couple of internal layers, and they're all fully connected. And you train this with 7,000 simulations, and you then look up all the remaining, any further answers you want from this network. And the graph, which is in the top and in the middle of the top, shows a lot of y equals x lines, and that's just looking up the answers. This is the testing phase of the deep learning, where we compare some independently calculated things with the prediction, with the inference from the network. And I wouldn't really be talking about this unless you saw y equals x clearly shown, and the error in the inference is comparable to the error in the molecular dynamics simulation. I should note that this was developed as a part of NanoHub, because this particular idea that you can look up the answers is pretty exciting for education, because we can now have students get the answers of complex simulations instantaneously. And that's obviously a good idea for education. Also, education has another important feature, namely, for this to be useful, this lookup, you better want to run several instances of this computation. And in education, we are going to run several instances, because we're going to have several classes with lots of students in each class. Here's just a news item I saw on the internet from some startup in Hong Kong, and they claim to have done for $150,000 what it would normally take 2.6 billion, and done it in a few weeks rather than 7 years. And this uses, again, a deep learning network, or deep reinforcement learning network, to capture the properties of potential drugs. And if you are familiar with the cheminformatics field, this is what's commonly called QSAR, quantitative structure activity relationship. And it's now, that whole field, as far as I can see, has been totally changed by the use of deep learning to effectively to be able to predict properties from the original structure. Here is results from DOE and my colleague Shantanu Jha. And another aspect, this is the one where we're building smart ensembles to explore phase space. You see a blue curve, which is the deep learning based system to explore phase space, and it gets to 93% of phase space in 23 microseconds computing, and then the sort of state-of-the-art computation in the field of traditional methods, Anton, takes much longer to get comparable coverage. And it's roughly an order of 10. This is only one order of magnitude improvement, but it's illustrative of the types of things you can do with deep learning, augmenting HP simulations. With colleagues Macklin and Glaser at IU, we're trying to use this for biology. And computational biology is particularly interesting, because there you're going to make a model of an organism which is made out of maybe millions of cells. We can replace each cell by a surrogate, a deep learning surrogate. Those are just a set of ODEs which we can learn. People have already done that for simple cases. And so we can really simulate much larger, more complex systems. So the last few minutes, I will discuss some slightly more possibly controversial idea, and that is we want to replace Newton by deep learning. So if you look at, say, a standard learning network and you feed in some values and get out an answer, that's an operator. So these operators, in some sense, are expressing the structure of the problem or the theory of the problem. And so let's look and see what these operators look like. And they sort of are interesting to me because they're completely different from the operators I was taught as a child, where I was told that if you want to represent numerically a differential equation, you should never use complex approximations. Typically, you should use a low-order approximation. And here we have approximations with up to 100,000 parameters, which seem to give reliable answers. So here is a very simple problem. It is a single particle moving in a Lennard-Jones potential, and we compare here the errors calculated. We use the so-called recurrent neural network, LSTM in particular, to represent this equation, and we use PyTorch or TensorFlow, and the PyTorch and TensorFlow predictions. The interesting thing is you can learn to do big time steps. The time step here is up to 4, which is actually 400 times what the molecular dynamics use, or 4,000 times, because that's probably 0.001 is the best molecular dynamics time step. And it does much better than the large time steps from classic simple molecular dynamics. Here we go to even much larger times, and here's actually just simple harmonic oscillator. And again, we get very low errors from using the neural net. And so obviously the neural net has learned Newton's laws, or at least the numerical approximation there too. And of course, when we apply this to more complex problems, it will get even larger gains, because we can learn the potential. I pointed out, if we learn the potential, we take potential calculations, we go like n to some power which is bigger than 1, and make them linear in n. And so we're going to get even bigger factors. So here is a little plot of speed up. And so here we're comparing the neural net with velocity Verloc, which is meant to be the standard one used for this problem. And we're just looking at the total time to integrate from 0 to 100. And for 3 different potentials, we get pretty uniformly a speed up of 30 to 40. And we can make the time step much bigger than 4 and get even bigger improvements. So if you look at this whole field of machine learning around HPC or for HPC, we can look at these different classes of applications. We saw the use of modest networks to understand structure of drugs. There's a lot of work, especially in materials as well as drugs. Surrogates, there's some initial results. The agent-based systems, I think, are really promising, because we can learn all those agents and really dramatically improve the performance. We can learn multi-particle potentials. That's been done many times. We can learn collective coordinates and guide ensembles. That's where you get these huge performances have been seen. I think we can also learn things like turbulence, clouds. Again, there's early work there, which looks quite promising. And then at the end, I mentioned the use of the recurrent neural nets to actually learn the time steps. The ones above the earlier ones are all using deep networks, which are not convolutional or just multi-layer perceptrons. And here, in the last 49 seconds, is the final slide. Well, it's relatively clear that parallel computing has a renaissance with big data. I pointed out that HPX got to be pretty well suited for big data. And then that ML for HPC will lead to remarkable discoveries. And I sort of say, for me, this is similar to what happened in parallel computing in 1981. I wandered around Caltech talking to the scientists, asking, what can you compute? And now we can try to do the same for machine learning. So ask, how can they use machine learning? And as I have 11 seconds left, I will stop there.